Welcome to today's paper reading. Today's paper is titled, Mind2Web, Towards a Generalist Agent for the Web. This paper was published in the 37th Conference on Neural Information Processing Systems, NeurIPS 2023, Track on Datasets and Benchmarks by Xiang, Deng, and colleagues from The Ohio State University. The Mind2Web dataset is the first of its kind, designed specifically for developing and evaluating generalist web agents. It includes over 2,000 tasks collected from 137 websites across 31 diverse domains. A key feature of this dataset is the use of real-world websites, which provides a more authentic environment compared to simulated ones. Additionally, the dataset captures a broad spectrum of user interaction patterns through crowdsourced action sequences. In an initial exploration, large language models, LLMs, were employed to build these generalist web agents. However, due to the size of raw HTML from real-world websites, a preliminary filtering step using a smaller language model was found to significantly enhance the effectiveness and efficiency of the LLMs. Despite showing decent performance on websites and domains not previously encountered, there remains significant potential for improvement in creating truly generalizable agents. The goal of building a generalist agent for the web is to create an entity that can operate on any website, handle the dynamic and complex nature of real-world websites, and support a wide range of user interactions. This presents several challenges, including the need for generalizability to websites not seen during training, the requirement to model dynamic environments accurately, and the ability to handle complex tasks that may require multiple steps. Existing solutions often fall short by being limited to specific websites, making strong simplifying assumptions about website behavior, and only supporting specific types of tasks, which limits their practical utility. Figure 1 showcases the diverse tasks and domains featured in the Mind2Web dataset. This diversity allows for testing an agent's generalizability in several ways. First, it tests the agent's ability to handle different tasks on the same website, as seen in tasks A and B. Second, it evaluates the agent's performance on similar tasks across different websites, exemplified by tasks A and C. Finally, it challenges the agent with entirely disparate tasks, websites, and domains, as illustrated by tasks D through F. This comprehensive approach ensures that the agent can adapt to various scenarios and tasks, reflecting real-world complexity and unpredictability. The Mind2Web dataset aims to bridge the gap between simulated environments and real-world websites. This is achieved by directly engaging with real-world websites and capturing snapshots of these environments. The dataset includes a diverse set of websites from various domains and crowdsourced realistic tasks that cover a wide range of functionalities. Each task in the dataset is defined by a high-level description, an action sequence required to accomplish the task, and web page snapshots that provide the environment for task execution. Figure 2 illustrates a sample data instance from our dataset, showcasing the three essential components. The first component is the task description, which outlines the high-level goal of the task. The second component is the action sequence, detailing the sequence of actions required to accomplish the task, each action being a pair of a target element and an operation. The third component is the web page snapshots, which provide the environment for the task in various formats including MHTML, DOM, HAR, and trace files. Actions marked in red indicate transitions to new web pages. Table 1 provides a comprehensive comparison of the Mind2Web dataset with existing datasets in the field. Key statistics highlight that Mind2Web encompasses 137 websites from 31 different domains, offering a broad spectrum for testing agent generalization. The dataset features an average of over 1,000 elements per web page, embedded within complex DOM structures, presenting a significant challenge for modeling. Unlike previous studies, Mind2Web emphasizes high-level task goals rather than low-level instructions, posing a realistic challenge for planning and grounding. MindAct employs a two-stage process to handle web page interactions. In the first stage, a fine-tuned small language model, LLM, is used to rank the elements on a web page, identifying a small pool of promising candidates. This stage leverages the efficiency of small LMs. In the second stage, these candidates are consolidated into a representative snippet, which is then processed by a large LM to predict the final action, including both the element for interaction and the corresponding operation. This stage capitalizes on the power of large LMs for accurate predictions. The candidate generation stage treats the task as a ranking problem, selecting the top KDOM elements that best align with the task description and current step. The task query is formulated by concatenating the task description with previous actions, and each candidate's textual representation is derived from its tag, content, and attributes. These are fed into a cross-encoder architecture to yield a matching score. In the action prediction stage, the top K candidates are used to construct snippets that are input to the large LM. The task of element selection is converted into a multi-choice question answering problem, enhancing generalizability and sample efficiency. The LM is trained to select from a list of options rather than generating the complete target element, and the process involves fine-tuning with a left-to-right language modeling objective. Figure 3 illustrates the comprehensive pipeline of Mind2Web, an exploratory framework designed to leverage the capabilities of large language models, LLMs, for processing complex web environments. The process is divided into two distinct stages. Initially, a fine-tuned small language model, LM, is employed to rank the multitude of elements present on a web page, thereby identifying a manageable pool of promising candidates. This pre-selection step is crucial for managing the computational load and feasibility of processing extensive raw HTML documents. In the subsequent stage, these pre-selected candidate elements are consolidated to form a concise, representative snippet of the web page. This condensed information is then fed into a large language model, LLM, which is tasked with predicting the final action. This prediction encompasses identifying the specific element for interaction and determining the appropriate operation to be performed. This dual model approach synergizes the strengths of both small and large LMs, optimizing efficiency and accuracy in navigating and interacting with complex web environments. Figure 4 illustrates the candidate generation module and the templates used for constructing the task query and candidate representation. The task query is formulated by concatenating the task description with previous actions. The textual representation of each candidate DOM element is derived from a combination of the element's tag, its textual content, and salient attribute values, as well as the textual representation of its parent and child elements. Each DOM element is paired with the task query and fed to an encoder-only LM through the cross-encoder architecture, yielding a matching score. This score is passed through a sigmoid activation function and optimized with a binary cross-entropy loss. At inference time, the top K elements with the largest logits are selected as input to the second stage. Figure 5 illustrates the process of action prediction using large language models, LLMs. The task involves converting element selection into a multi-choice question answering, QA, problem. The top K candidate elements are pruned from the web page snapshot to construct snippets that are input to the LLM. The candidate set is partitioned into groups, each containing up to 5 elements and a none option. During training, the model is fine-tuned using ground truth actions and a left-to-right language modeling objective. During inference, the top K candidates are divided into clusters of 5 options, and the process repeats until a single element is selected or all options are rejected by the model. Table 2 presents the main results of the study, focusing on the generalization performance of models across different settings. The classification baseline employs the BRTB, while the generation baseline utilizes FLAN T5B. The table reports macro averages for stepwise metrics, providing a comprehensive view of the model's performance. Notably, GPT-4 was evaluated on 50 tasks with top 10 candidates due to budget constraints. Detailed results on the 50 task subsets for all methods are available in Appendix D.3, offering a deeper insight into the model's capabilities in various scenarios. The experiments are conducted under 3 test settings: test cross-domain, test cross-website, and test cross-task. In test cross-domain, the model is evaluated on 2 top-level domains with 912 tasks from 73 websites, focusing on its ability to generalize to entirely new domains. Test Cross Website involves 10 websites from each remaining top-level domain, containing 177 tasks, assessing the model's adaptability to new websites within familiar domains. Test Crosstask randomly splits 20% of the remaining data into 252 tasks from 69 websites, evaluating the model's performance on unseen tasks within familiar websites. Data preprocessing involves applying simple heuristics to clean raw HTML documents, reducing the average number of elements from 1,135 to 580 while maintaining a high recall rate of 94.7% for the target element. The evaluation metrics include element accuracy, operation F1, step success rate, and task success rate, providing a comprehensive assessment of the model's performance. Figure 6 presents the step success rate per website, categorized by the 3 different splits: Test Cross-Task, Test Cross-Website, and Test Cross-Domain. The data is displayed from left to right, focusing on websites that have undergone more than 3 test tasks. This visualization helps in understanding the performance variations across different testing scenarios. Notably, there is no significant difference in performance between the Test Cross-Website and Test Cross-Domain settings, suggesting that the challenges primarily arise from the diversity in website designs and interaction logic rather than domain specifics. The development of autonomous agents for web and mobile applications has faced limitations due to the types of tasks and environments they can handle. These agents are often confined to simplified simulation environments or limited to a narrow set of domains. In contrast, large language models, LLMs, have shown significant advancements, with models like GPT-3 and PaLM demonstrating capabilities in few-shot learning and in-context learning. These models can adapt to new tasks with minimal examples and without the need for explicit retraining. Additionally, our work aligns with grounded language understanding, which maps natural language onto executable plans in real-world environments, overcoming the limitations of well-structured schemas. The current data collection for Mind2Web is limited by its predominantly English language and US-centric website selection, as well as the annotator source from Amazon mTurk, which may introduce biases. Additionally, the system currently models the web environment using only textual context, neglecting crucial visual information. Furthermore, the interaction dynamics are modeled by encoding each web page independently, with limited historical context, which may not fully capture the dynamic nature of web interactions. The current design of Mind2Web requires a single upfront task description, with no provision for mid-task adjustments or interactive feedback, which may not reflect real-world usage. Evaluation is currently conducted in offline cached environments, which can lead to false negatives due to the lack of multiple paths for task completion. Finally, while the deployment of such agents holds great potential, it also raises significant safety concerns, including the management of sensitive actions, ensuring transparency and user control, and addressing potential cybersecurity risks. In this work, the authors introduced Mind2Web, the first dataset specifically designed for developing and evaluating generalist agents for the web. This dataset serves as a valuable platform for the research community to advance towards creating more capable web agents. Additionally, the authors proposed Mind2Web, an agent that utilizes the power of large language models to effectively tackle various tasks. Looking ahead, the authors envision a wide range of promising future directions, including the integration of multimodal information, reinforcement learning with feedback from real websites, and the development of specialized language models tailored for web understanding and action taking. Thank you for watching.